Okay, in this video I'm going to talk about nucleophilic substitution. Nucleophilic substitution is when you have a halogenoalkane. Now the halogenoalkane is quite a reactive molecule because the bond between the carbon and the halogen is polar due to the electronegativity of the halogen. And not only is it polar, the bonds are relatively weak, they can be broken in the presence of the right species. And the right species in this case is usually a hydroxide ion, which you can get from any strong base like sodium hydroxide, potassium hydroxide. It could potentially be water. It also works with water. And what happens is you substitute the OH minus for the halogen and you produce an alcohol. And obviously the halogen is going to leave as a halide ion. Okay, so that is nucleophilic substitution in a nutshell. Standard levels, you only really need to know the reaction and be able to balance equations showing this. You don't need to be able to do the mechanism for this. High levels, you need to know the two different mechanisms, first order and second order nucleophilic substitution mechanisms to show this. So first order nucleophilic substitution this happens if you have a tertiary halogenoalkane. Okay, so if you have a halogenoalkane, I'm going to keep using chlorine as my example, and I have carbon atoms on all of the other positions around this central carbon. Okay, so this is a tertiary halogenoalkane. Now, the presence of these other carbons around here allows stabilization. It allows electrons to be moved inwards towards that central carbon. And so this first step, which is heterolytic fission, is where the polar bond between the carbon and the chlorine breaks, with both electrons moving onto the halogen. And what that forms is a carbocation, which is positive, and a halide ion. Now, this is the slow step, the rate determining or rate limiting step out of this two-step process. Once we form the carbocation will very quickly attract a nucleophile, for example, the hydroxide ion. And the nucleophile has a lone pair of electrons. There are other molecules that can act as nucleophiles as well. Obviously, we talked about water. You can also use the nitrile group, or you can use ammonia. The nitrile, so the cyanide ion Cn minus or ammonia, which is NH3, they can work as well. However, they're not in your syllabus anymore. So we'll stick with the hydroxide ion. So the hydroxide ion, with its lone pairs of electrons, we can have a bond forming with that central positive carbon, the carbocation. Notice that the curly arrow goes from the lone pair on the nucleophile to the positive charge on the carbocation here. And it will form that bond, producing an alcohol. Now notice the total products of this reaction, we've got the halide ion from the first step, and we've got the alcohol from the second step. So if you're showing this mechanism, you must always show both of these products. This second step is a fast step, it's not rate limiting, and therefore the only substance whose concentration is going to be affecting the rate of the reaction is our halogenoalkane. So the rate of this process is determined by the concentration of the halogenoalkane. The concentration of the nucleophile plays no role. So that's first order nucleophilic substitution. It's a two-step process. It's a relatively fast process. This mechanism is obviously it happens with tertiary halogenoalkanes. It's favoured by a polar protic solvent which will stabilise our carbocation. So something like water, something which is able to do hydrogen bonding. The second order nucleophilic substitution this happens if you have a primary halogenoalkane. So a primary halogenoalkane, we have, again we're going to use chlorine, but we have hydrogens on at least 2 of the positions around that central carbon. There might be a carbon on here. I'm going to put a carbon here for the sake of argument, but we've got at least 2 hydrogens on there. Now, hydrogens are much smaller than carbons, and so they're not going to get in the way of a molecule reacting directly to this central, slightly positively charged carbon. Steric hindrance is basically where you have a large enough group to block any attack on this molecule. So in the case of our tertiary halogenoalkane, these surrounding carbon groups are too big for any attacking species to get in from the other side in a process known as steric hindrance. Here we don't have that. So our nucleophile, which I'm going to put over here this time, with its lone pair of electrons, so the hydroxide ion here, is able to directly attack the other side of this carbon from the chloride, okay, from the halogen group here. Now, obviously, in a 3-dimensional molecule, it will be attacking from directly opposite. Since it's a tetrahedral molecule, it will attack from between the 3 other bonds. Here, since it's 2-dimensional, it doesn't really look like that, but that's what's happening. So the nucleophile attacks onto this directly onto the central carbon before this bond breaks. What then happens is, as this bond starts to form, using the lone pair of electrons from the nucleophile, the bond from the carbon to the chlorine will then start to break. And you will end up with a transition state. You'll end up with a transition state where both the nucleophile and the halogen are still attached to that central carbon. Now, this nucleophile is bringing a negative charge with it, so we must show the negative charge on the transition state, and we show that the whole thing is negatively charged by putting it in square brackets with the charge outside. And these dotted lines here show the partially formed bond between the nucleophile and the carbon, and the partially broken bond between the carbon and the halogen. So that's kind of the first half of the reaction. It's not a step. The whole thing is a single-step process. And then the reaction then continues beyond the transition state, where this bond on the left will continue to form and this bond on the right will continue to break until we end up with our product. With our OH group attached to the carbon, so making our alcohol, and our halogen has now completely left as a halide ion. Now notice we have exactly the same products, the alcohol and the halide ion, as we did above, but this is a single-step process. And since it's a single-step process, the concentration of both of these molecules is going to play a role. So both the nucleophile, the hydroxide ion, and the halogenoalkane, if we double the concentration of either of those, it's going to be able to double the rate. So our rate expression in this case is going to include both the halogenoalkane and the nucleophile. And hence, the total order of the entire reaction is going to be second order, because we add our 2 orders of reaction together to get the total order of reaction here. So that was nucleophilic substitution. The second order process is slower than the first order process because this requires a much greater activation energy to happen, and so it's a slower process. This second process is favoured by a polar aprotic solvent, so one which can't form hydrogen bonds but is still slightly polar, which will therefore inhibit the formation of carbocations, but instead allow it to go through this and it will stabilize the transition state. Now, the key factor that allows this is the lack of steric hindrance, allows second-order nucleophilic substitution, which is why we get it with primary halogenoalkanes. For first-order nucleophilic substitution, the key factor here is the stabilization of the carbocation by the electron inductive effect. Tertiary halogenoalkanes will undergo nucleophilic substitution faster than primary due to the relative rates of first-order nucleophilic substitution to second-order. First-order is quicker, second-order is slower, so that's why these tertiary halogenoalkanes will react faster than primary ones. The other factor that you need to bear in mind is the identity of the halogen in the halogenoalkane. Now, although it is true that the more reactive halogens like fluorine and chlorine will have a more polar bond, the overriding factor is in fact the strength of this bond between the carbon and the halogen. And since as you go up the group, the more reactive halogens have stronger bonds with the carbon, it's more difficult to break this bond, which slows down the rate. And therefore, the lower in the group, the less reactive the halogen, the more readily they undergo nucleophilic substitution. So an iodo compound is going to react much, much faster than a chloro compound due to the strength of that bond between the carbon and the halogen.